Yes. So I'll just give a small, background of what we want to do here. The previous two webinars that we have done, essentially, we spoke about conduction. We spoke about the primary modes of heat transfer in much more detail as an introductory webinar. And today we are talking about convection. The idea is to build up to radiation and then conjugate heat transfer. Once we get to conjugate heat transfer, I want to explain the implications of how each mode of heat transfer can be applied using a particular CFD software package. The computational fluid dynamics or the computational part of fluid dynamics essentially came about for understanding heat transfer for the most part, because every single industry you want to go to, mechanical, aerospace, chemical engineering, biomedical, etc., everywhere we will see that there is some amount of heat, and you want to manage this amount of heat no matter what. So managing heat is all about understanding where heat is generated, how you can take it away from that one place as efficiently as you can, and then understanding how much energy do you have to expend to remove that heat away from that one place. Are there any increases in surface area that you can do which will help you out in increasing your heat transfer, so on and so forth. So making really cool design choices, so to speak, to ensure that your thermal management is done really well. So on that note, I'll just begin with the topic at hand today. Today we have convection. I want to just speak about heat transfer from a fluids standpoint more than your solids itself. So essentially we'll cover a lot of topics, all the way from how convection differs from your conduction, and what are the different equations that we are actually going to work with. Just to give you a short background about myself, my name is Siddhartha. I've done my MS, Masters in Aerospace Engineering, with the major in fluids and propulsion. I've worked on high-speed combustion devices like the rotating detonation combustor. I've helped develop thermal systems for our experimental rig as well for the said combustion device here. I have good expertise now in running open form, primarily helping organizations, companies with switching from a commercial software package to open form, helping them with the workflows, helping them with proof of concept, etc. And I have a good background now in technical trainings, primarily for CFD driven product design. I work with Wrenchwise. I'm the business unit head for mechanical as of now. Cool. Talking about the contents itself, we'll start with fundamentals, then we'll talk about the base physics and some dimensionless numbers. Dimensionless numbers are really important when we talk about convection specifically, and there's a load of confusion that comes in this particular area itself with dimensionless numbers. Then there is the calculations, the engineering level calculations. There are a few correlations that you could still do and get away with initial design choices, and the comparisons within that itself. And ultimately we'll just talk about the real world application, the safety, and then what strategies you should be using for your CFD. Cool. So let's start with fundamentals itself. Talking about convection itself, so on the left we have conduction. Conduction is limited by the material itself, like what type of material are you going to use. It will have its own material properties. Be that as it may, we saw previously that thermal conductivity may or may not be isotropic, is that in that it may or may not be equal in all directions, but still it's a material property that you can measure and can assign in your solver. Convection is essentially conduction plus motion, where fluid will continuously sweep away the heat and temperature. It will essentially replenish your surface with the cool fluid. That's the whole plan here. So this bulk fluid motion is essentially why a fan or pump is generally used more effectively than static cooling itself. A very small increase in fluid velocity can very dramatically increase the effectiveness of heat transfer through the fluid itself. And ultimately there is radiation. We already know radiation is something that is dominating at higher temperatures, and radiation does not really require a medium. as compared to your conduction and convection, but radiation still comes into play at higher temperatures when your batteries primarily tend to fail. That's the whole idea. So where does convection essentially fit? Conduction, your molecules have to collide and then transfer the heat. It is limited by its properties. Convection is driven by the flow itself. Ultimately, the fluid has to carry some amount of heat, and radiation, it is only valid when you have higher temperatures. Now, of course, if velocity of your fluid increases, convection is essentially going to dominate in those particular areas because heat transfer will be more effective. We'll see about why that is the case. If velocity is higher, why do we have more heat transfer? So talking about convection itself, there are two different types of convection we always talk about. There is the forced aspect of it, there's the natural convection aspect of it. The way to think about it is quite simple. Whenever you have an object that is hot, it will try to heat up its surrounding areas, its surrounding bodies itself. So with natural convection, your body itself is at rest, and surrounding fluid could also be at rest at time t is equal to 0. But if the body that is kept here is at a higher temperature, the surrounding air will heat along with it. Its density will reduce and it will just rise up because lighter air is going to rise above your heavier air. That's natural convection, plain and simple, because it will rely solely on density changes caused by heat. This is your buoyancy. Then there is the forced convection. This is what you want in all of your industrial applications. We use external energy. This can be pumps, this can be fans to drive your flow. The difference in heat transfer coefficient is quite vast. The forced heat transfer coefficient could be, a higher number, somewhere between 100 to 10,000 or even higher, depending on what case you're working with. But natural convection is limited to pretty much 5 to 50. The idea being that when there is not enough fluid motion passing against the wall, which is at higher temperature, your heat transfer coefficient would be quite lower. For forced convection, we generally are limited by the amount of energy we can supply to these cooling systems. Primarily high power applications like your electronic vehicles, etc., these tend to use your forced convection, whereas natural convection generally for low power silent electronics like your phone charger, etc., these you can still get away with when it comes to natural convection. So this is a very simple understanding of what buoyancy is. You have cold plate on the top, you have hot plate on the bottom. If air surrounding it is going to act accordingly, the temperature is higher on the bottom, temperature lower on the top, the air surrounding it will essentially try to rise up in this plume fashion. This is your natural convection. Now, coming to this aspect of natural versus forced itself, idea is again driven by density. Your air particles will move alongside with it. It will gain its own energy. But when driven by a pump, the heat transfer coefficient very rapidly increases. The cooling power of your system will increase drastically. But there's also a caveat that we'll talk about later. The biggest choice that you want to make is the material or the working fluid itself as to which fluid will, be the most carrier of heat away from the surface. Generally speaking, velocity is the biggest lever that you can play with. Design choices can vary all the way from what surface area you want to do, what pressure drop you will have across your entire cooling channel, what type of coolant you will use, etc. But biggest driver or biggest control that you may have is primarily your velocity at the end of the day. And today, at least in the design space, product design space, we are limited by very stringent requirements of lower noise and lesser power consumption, etc. That's where smarter technologies need to come in. We can't just get away with adding a pin across the cooling channel and then expecting that the heat will be taken away. Rather, a smarter way of, let's say, adding a certain phase change, adding a certain vapor chamber, adding different cooling circuits, and adding certain solid particles inside your cooling channel, so on and so forth. All of these need to be implemented even today. Great. So talking about heat transfer in fluids itself, there is the magic parameter that we want to talk about here. This is the heat transfer coefficient. Unlike your conduction, the heat transfer coefficient is a system property, meaning that you can't really look it up on a book, or you can't Google for it saying that, hey, for so and so scenario, water is flowing inside a pipe. What is my heat transfer coefficient? Can you give me a value? It's not really possible. So the three different levers you currently have is your heat transfer, the Q, this is in watts, then the surface area, this is the geometric lever. You can add fins, you can add micro channels, or you can do the temperature difference between the wall and the fluid itself. In that, in your cooling circuit, you are expecting the fluid to reject its heat and then send the fresh, cooler fluid back into your circuit and stuff like that. So heat transfer coefficient, rather, you can't really determine. It's a very simple system property that you need to solve for using either analytical or computational methodologies. So what exactly is this heat transfer coefficient? It depends on these properties here: fluid velocity, geometry, fluid properties, turbulence, so on and so forth. So Newton's law and this magic parameter, you can control the area with adding your fins or microchannels, etc. Or the temperature difference could still be controlled. As I said, the fluid can reject its heat outside, but the heat transfer coefficient, this is something again you'll have to calculate for. Oh yeah, and the cooling effectiveness, ultimately, as I said, material matters a lot. Having a more dense sort of a liquid essentially helps you scale down your volume itself, because lesser surface area is required where fluid will be in contact with the hotter surfaces. So liquid cooling is far preferred to air cooling. Of course, it has its own hits and misses, so to speak, primarily coming to leaking in your cooling channels, the amount of noise that it will generate, and so on and so forth. So with that, I'll just take small pause and we'll send a poll here. So unlike thermal conductivity, which is constant material property, how is heat transfer coefficient best classified? Is it also a constant material property? It's a system property. It's a fixed ratio, or it's a radiation constant. So now we move to the physics and the dimensionless numbers themselves. I want to dive a little deeper into the concept of boundary layer, the concept of thermal boundary layer, what it is, why do we care, etc. Coming to the concept of boundary layers itself, this is fluid mechanics 101. Your fluid, when it comes in contact with a solid wall or a boundary, it will try to stick to that boundary, and the closest layer near to that boundary will always be at rest, and the fluid layers above it will try to rub past it. That's where you will see this configuration of the velocity boundary layer that you can see here with delta. Now, there exists in heat transfer another type of boundary layer. We like to call it the thermal boundary layer, or the delta underscore T that you see on the right hand side here. The idea being, as you move away from the wall, there will be a temperature gradient that you are interested in. You are much more interested in how this fluid is carrying away the heat from this particular wall on the bottom. So the effectiveness of heat transfer, and to be very clear, the fluid taking away heat from this particular wall, this is the heat transfer we're talking about, entirely dependent on steepness of this temperature gradient at the wall itself, or rate of change of temperature as you keep moving away from the wall. Idea is, if you are moving fast, this boundary layer becomes thinner. If you are moving slow, the boundary layer becomes thicker. Why does that happen? The reason why that happens is because when fluids move slower, the fluid that is closest to the particular wall is going to push some amount of viscosity, some amount of friction to its subsequent layers, and the subsequent layers act as a sort of a blanket on top of all of your subsequent layers. And idea is, the way in which this wall will transfer its heat to the first layer of the fluid itself is going to be conduction, in that since the fluid is at rest, the heat will be transferred by the wall to the fluid particles by the virtue of conduction, and this conduction, this heat that is present on the first layer needs to be transferred to subsequent layers, and it needs to be carried away. If the fluid is moving slower, this process happens very slowly. That's why your thermal boundary layer is going to be thicker. And we know now that solids are really good conductors, or so to speak, metals are much more better conductors. And at any given day, solids are much better conductors than liquids or than gases for the most part. This is because of, lattice structure available, free ions available for metals. So solids have better conductivity compared to liquids or compared to gases. They have freer molecules. There's no lattice structure. There are no free ions. So the transfer of heat is primarily going to be through molecular collisions, and it will be very slow. So the thermal conductivity, so to speak, of your fluids is going to be lower. So again, end of the day, faster the flow, better the heat transfer. Slower the flow, lower the heat transfer. That's the general thumb rule that we are working with. So with respect to the boundary layer itself, we have no slip at the wall itself. And as we look at the closest layer, it will be pure conduction. By virtue of this conduction, for a slower flow, the boundary layer will be thick. For faster flow, the boundary layer will be thin, and your heat transfer coefficient will be so near to the wall. If your U infinity is fast, the thermal boundary layer is going to be squeezed near to the wall. That's the whole idea. Now, again, when it comes to boundary layer theory, we talk about this concept of meshing as well with Y+. I'll briefly like to touch upon it. Again, we've discussed this previously, but I'll just tell you briefly again. So Y+ is again this dimensionless number, this measure of how far you're away from a particular wall. We choose Y because in our notation, horizontal is X, vertical is Y. So a non-dimensional number away from wall is Y+. Why non-dimensional? For the most part, CFD is applied to varied amount of applications, and you need a generalized way to say, hey, for a distance away from my wall, I will measure how my fluid is behaving like. So we say that till a certain distance, the fluid is going to be laminar. Beyond that, it will be starting to become turbulent, and beyond a certain number, it will be fully turbulent. So to quantify, or to be able to quantify these measures for an airplane, or for a flow in a pipe, or for ship moving on top of your ocean, the idea essentially remains the same, that the non-dimensional distance Y+, if it is between 0 and 5, let's say, the flow is going to be laminar. 5 to 30, it's going to be transitional. 30 and above, it will be fully turbulent. So that's precisely the reason why we are using this notation of Y+. The logic behind understanding why we want more cells near to the wall here, or having your first cell layer center be at a particular Y+ number, is to ensure that your CFD solver is able to capture the sharp changes near to the wall as accurately as you can. That's the whole idea. So if you have lesser cells near to the wall, this will cause a whole lot of mess. We'll just talk about it in just a bit. Great. So again, just to circle back to this, high velocity, your turbulence, it will cause chaotic mixing, and which will essentially thin your boundary layer. This thinning is going to maximize something we call the Nusselt number. Therefore, thin boundary layer essentially indicates high Nusselt number, meaning that convection is more dominant than the conduction here. Thick boundary layer, this is a thick blanket itself. Heat will struggle to escape your flow. Thin boundary layer is a thin sheet. Heat will escape quite easily. So when having a choice between low velocity and high velocity for heat transfer, always choose a higher velocity. Cool. Now we talk about how do we quantify our flow itself. When we talk about quantifying, we talk about having a number which will tell us something about the flow itself, right? So the first thing we have, this is a Reynolds number, quite famous. This is defined as this flow regime indicator. It will tell us if the flow is smooth, laminar, or if it is chaotic, turbulent. It will compare the inertial to viscous forces, this ratio of density times velocity times this characteristic length divided by this viscosity, dynamic viscosity. If you want kinematic, you can just remove the density part there, and UL by nu we'll just have that. This also varies for internal and external flows. For internal flows, your Reynolds number can be a certain number, and below that, your flow will be laminar. Beyond that, the flow will be turbulent, and same applies for external flows as well. For internal flows, this number is much lower because you are bound. The flow is essentially bound, and there are more chances for this chaotic nature to come in between. That's the whole idea. Another number that we are also interested in, this is Nusselt number. As I said before, it measures essentially how better your convection is compared to simple conduction. There's a very good link between the two here with Reynolds number and Nusselt number, which is essentially how fast your flow is. Higher Reynolds number will lead to chaotic mixing, which will maximize your Nusselt number. That's the whole plan. So this ratio of convection to conduction, again, laminar flow, Nusselt number somewhere between 5 to 100, turbulent somewhere between 500 to 5000 and above, so on and so forth. So ultimately, higher velocity, higher your Nusselt number. That's the whole plan. So Reynolds number, ratio of inertia to viscosity. Lower the Reynolds number, laminar. Higher the Reynolds number, the more chaotic and turbulent. Then we have this Nusselt number, ratio of convection to conduction heat transfer. So high Nusselt number, meaning high efficiency, or better the heat is being carried away by your particular fluid. So with high Reynolds number, this chaotic mixture, the boundary layer will be much thinner, which will lead to higher Nusselt number or maximum Nusselt number. That's the whole plan. There is one other number we need to talk about. This is more to do with spread of your properties. We have spoken about diffusion previously. Diffusion is how quickly a properties will spread across in different directions. Prandtl number essentially compares how fast your fluid is going to spread versus how fast the heat is going to spread. The best way to understand essentially is to, again, if you tend to look at it that way, the effect of a perfume, let's call it, the perfume is going to be spread in a particular direction in your particular room. It will still reach you after some amount of time because the perfume particles will diffuse in the entire room and it will reach you no matter what. That speaks about the momentum diffusivity, or how quickly your perfume particles are reaching you essentially if they are spread in somewhere a corner of your room. Thermal diffusivity essentially talks about if you have a hot block of iron kept in your particular room, how fast will that heat be spread across the particular room and taken away from that hot block itself. So the ratio of this momentum to thermal diffusivity is what we call this Prandtl number. When we compare two different fluids, let's say this air and water has higher thermal conductivity, about 23 times higher. When we combine this water's density and the conductivity, liquid cooling is approximately 50 times more effective than air cooling itself. This is, pretty much what we want from a good thermal management system, that if you are limited by the heat transfer through the area, you have added enough pins, added enough cooling channels, the only thing that will save you is the right choice of fluid. And again, the dimensionless numbers like your Prandtl number, etc., these will help you in choosing the right fluid for your particular case. So a higher Prandtl number, better for your particular case. Again, this of course has its own limitations. If you look at oil here, Prandtl number close to 1000, but it is viscous and the diffusion is quite slow. So in such cases, the choice of fluid may not be best when it comes to just the sheer number of Prandtl number being higher. You want to take a look at other effective measures here as well, or the metrics here as well. So Prandtl number, momentum to thermal diffusivity. This is the stickiness or drag, and this is the heat or spread. Idea is with air, if your velocity is higher, the diffusion will be, higher, but with water, it will be a mix of both. So thermal conductivity of water much higher. So water is good, in terms of being a coolant, so to speak. Let's talk about the calculations as well. So we've seen so far that there exists this heat transfer coefficient. There exists the dimensionless numbers here. that we can still figure out through certain means. Prandtl number you can still get for a particular fluid. How do you find out this Nusselt number? There are a few correlations that are present. For laminar, this is the Paulhausen. The Nusselt number is approximately proportional to Reynolds number power 0.5. Whereas for turbulent flows, there is the Ditus-Bollert correlation. This is Nusselt number equals 0.023 times Reynolds number power 0.8, Prandtl number power 0.4. So when your regime is essentially turbulent, that means and Reynolds number being equivalent to a velocity lever, so to speak. So because your heat transfer coefficient is proportional to velocity to the power 0.8 now, velocity is essentially your strongest lever or strongest control that you can use. So if you double your velocity, you get roughly 1.74 times increase in your cooling itself. So if we double our fluid properties, let's say the Prandtl number, we only get 1.32 times the increase essentially. So yes, choice of fluid is also important. The Prandtl number power 0.4 is still very important, but again, velocity is your strongest lever for enhancing convection no matter what. So laminar flow, Nusselt number is proportional to this. Turbulent flow, Reynolds number power 0.8. So turbulence will scale this aggressively, power 0.8. So if we take a look at a laminar flow versus a turbulent flow, we'll see that the H will increase much more when it compares to a laminar flow, right? So fluid Prandtl number, heat transfer coefficient may not change as much, but with velocity, heat transfer coefficient will change by a factor of 74%. So velocity, again, still is the strongest lever that you have. Let's take a look at the cooling effectiveness as well. So when it comes to displaying such type of data, I'll just talk about this logarithmic scale that we have on the bottom as well. Logarithmic scale or a log scale is a way of displaying your data that will cover massive range of values. So from very small of 1/10 all the way to this 1 lakh in a very small, compact, manageable space essentially. So unlike a linear scale, like your scale, your ruler essentially, it will increase by adding the, or multiplying the bottom axis by a particular factor, so that it will increase like tenfold like it is doing right now on the bottom. The reason why we're doing this again is because the properties themselves are changing so drastically. So we use the logarithmic scale to show this massive jump in the performance. So the first thing, natural air that we have, this is bottom tier from 5 to 25. Generally, much lesser heat transfer coefficient here. Coming to forced air, this is a middle tier, 25 to 500, still a little bit better. But the forced convection of water, this is top tier, somewhere between 500 to 10,000, based on how much you can increase the velocity inside your cooling circuit, roughly 50 times better than your particular forced air itself or the natural air itself. So the extreme limit of how you want to do it is through phase change itself, which can be boiling, which can be a different phase change material of a resin, of a wax, so on and so forth. This can reach to a 1 lakh watt per meter square Kelvin still, but for most practical applications, we are still limited to using a particular fluid. This can be, for the most part, something like a glycol or a water glycol mixture is what we tend to use. So what are these? Okay, air is still a good contender because air is something that you don't have to, carry alongside with you. But liquid is something that gives you really good performance. As we saw, it has very high heat transfer coefficient, and you can build these compact channels with attaining higher thermal stability ultimately. But for the most part, liquid cooling is limited by, for the most part, it is the plumbing complexity of how you are going to move a fluid from one point to another, especially in very small channels, is a big challenge. And it essentially introduces leak risk, especially near areas where, let's say, your battery is going to sit or electrical component is going to sit. If this is not planned well, or if this is not manufactured well, which generally tends to be the case, where a certain manufacturing defect or using a particular seal which is not of the right grade, so on and so forth, could still be disastrous to your system. So it introduces a lot of these complexities, and it is of higher cost as well. The amount of energy required to pump your liquid across the cooling channel, it will still be high when compared to your air. But liquid cooling is still going to be useful for performance or power systems, primarily your EVs and high power charging, etc. But for the most part, air is still a good contender. It is moderate heat transfer coefficient. It is simple, low cost. There is no leakage, issues at all here. This can still be used for power tools, for budget EVs, for low duty cycles, etc. So we still have, areas where air can still be applied and liquid cannot be. So liquid cooled versus forced air, heat transfer between 100 and 500. But liquid cooled, we can still reduce the volume by 40%. For a particular heat load of 150 watts, liquid cooled can still be managed here, but air cooled will not be, because the higher your velocity that you want, it will be impractical in terms of noise, vibrations, and the amount of power required to remove that heat load of 150 watts. So again, pick and choose here which one do you want to design and how meticulously can you actually design for your particular product. Cool. We'll stop for another poll here. So in a turbulent flow regime, if you double the fluid velocity, roughly how much does the cooling performance increase? So it increases by 74%. Good job. So now let's talk about the real world application and the safety itself. We'll talk about again 150 watt load, and we'll try to keep the cells under a certain temperature and understand what that is going to be. So the scenario is we have 150 watts of heat load coming from 10 different cells here. The idea is we need to keep these cells under 50 degrees Celsius. We want to select a flow rate of 2 liters per minute, and the fluid will be like a 50-50 ratio of water and glycol. So first thing we do, we want to calculate the Reynolds number itself. It will be 3100. And since this is internal flows, 3100 is still turbulent. So using our correlation, we can approximately get a heat transfer coefficient of 3000 watt per meter square Kelvin. So once you have the heat transfer coefficient H and you have the heat load, you can easily calculate the delta T that you actually want. The wall temperature could stay somewhere around 39.5. Given the correlation that you have for turbulent flow, the Titus boiler will still work for your particular case. So for the given flow rate that we are working with 2 liters per minute, we can estimate that the wall temperature could stay at 39.5 degrees Celsius. We could maintain safety limits with negligible pump power, so to speak. Now, if the same scenario we want to use air in this particular case, so applying the same 150 watt for air with a transfer coefficient of 60, let's say, the cells would overheat. We would need impractical wind speeds of more than 5 meters per second. A point of contention that I have where people try to stop and say that, hey, 5 meters per second is still low, but think about it this way. Average height, let's say at least my height, is close to 1.77 meters, and the wind speed that we're talking about, 5 meters per second, is very quickly going to move past me in the, very quickly. It will move past at least 2 people stacked up on top of me in a second. So that's still quite fast. So 5 meters per second of wind speed is no joke. Even at that speed, the amount of power that will be required to pump your amount of air and the amount of noise that it will cause from the fans itself, it will be quite impractical. So this will give rise to a thermal runaway problem, where again, you will have your battery go beyond a certain temperature and it will start, the anode cathode will start reacting, the separator wall will go away, and they will react within each other, causing these explosive exothermic reactions, and the cell will very slowly increase its core temperature to greater than 800-900 Kelvin. And in such scenarios, the conduction heat from the cell to the nearby areas is still going to be slow, but convection from the hot gases that will release is going to be very fast. Because again, remember, the hot gases, they have freedom essentially to move in all directions and diffuse in all particular directions, compared to your conduction, which is still limited by contact of your multiple solid bodies being together. So convection is approximately going to accelerate your failure propagation by 4 to 8 times. So we absolutely require thermal barriers to block this particular gas flow, not just physical contact itself. So coming to limits of this air cooling itself, for the most part, you are limited by the heat transfer coefficient of air itself. You cannot physically keep increasing the velocity of air. Coming to the thermal runaway aspect of it, conduction may still take a while, but convection will be quite fast. So adding your heat shields here is going to be critical when it comes to saving your battery pack from getting into thermal runaway. Cool. I'll quickly bookend this with some CFD strategies and the summary, and I'll showcase one case setup as well, or rather I'll showcase the result of it. Cool. Biggest takeaway when it comes to CFD is to solve for heat transfer coefficient accurately, your mesh needs to resolve the boundary layer appropriately, because you want to capture the temperature gradient as properly as you can. Generally speaking, there exist these two areas of solving your CFD, where it is wall resolving versus wall modeling, or what we like to call wall functions. Idea is, resolving means that you are going to sit there and then resolve it or calculate for it. So wall resolving, this is high fidelity approach. It resolves the viscous sublayer, but it is computationally expensive because you are increasing the number of cells near to the wall. So as you can see in the image here, more cells very closely packed near to the wall, and they are increasing at a particular growth rate. The reason why we want this is because we want better capture of our gradients. I have a question here. Is there any formula for calculating first cell heat transfer for thermal boundary layer? I'm afraid not, or at least not one that applies for every single case. These exist for very simple problems like a flow over a heated flat plate, etc. But I mean HITA. Yeah, there are formulas available for Y+. So the best thing I can do for you, we have a few tools coming in on our website itself. I have a Y+ calculator that is coming in, which will help out. But generally speaking, for calculating Y+, you have the formula distance away from the wall times the friction velocity divided by the kinematic viscosity, if I'm not wrong, where the friction velocity, not for boundary layer, for thermal boundary layer. Okay. No. For thermal boundary layer, no. You can't really. Okay. Let's look at it this way. When I say resolve a boundary layer, we are primarily talking about momentum boundary layer itself, because there is at least a way to estimate for yourself where your first cell layer height could be. But thermal boundary layer is something that is entirely dependent on the flow itself. And this is something that you have to solve for iteratively, because you cannot really estimate, or you don't really have correlations beforehand to figure out how your thermal boundary layer will essentially look like. So there's no formula as such for calculating first cell layer height for a thermal boundary layer, no. Another very interesting question I tend to get, how do you choose, or how do you get the Y+ correlation for like a natural buoyancy or a natural convection case? These are also interesting questions that I will discuss in the next class, because we're already 10-15 minutes away. So yeah, just to answer your question, no. For thermal boundary layer, no. There does not exist a correlation or a formula, at least not that I'm aware of. If I do see something, I'll mention it in the next webinar. Cool. So yeah, wall resolving, this is high fidelity, it is computationally expensive. The other side of it is the wall functions. If your Y+ is greater than 30, this is much faster, empirically approximated, and generally used for standard flows. It will do the job. It will give you an estimate. If your goal is to have faster product design, go for wall functions. And once you come to a certain design envelope of, hey, this works for me, let me find the best. So that's where you want to do high fidelity. That's where it will help you. Uh, Best practices, the biggest challenge with meshing for thermal analysis at least is having more number of layers. Having at least 10 to 15 of these prism layers will really help out. Growth ratio 1.2 close to, it will help capture the gradient. But meshing remains a bigger challenge because your geometry is not going to be a simple flat plate. Your geometry will have multiple elements. It will have small elements, it will have big elements, it will have curves, sharp edges, etc. So creating prism layers for all of these areas remains a challenge, but nothing that you can't really plan for. It will take some time, but you can get it done. Cool. So meshing for accuracy. So away from the wall, you want for higher accuracy, you want your mesh cell height at least to be near to this viscous sublayer. So wall resolving y plus less than 1, and wall modeling. Yeah, and for wall modeling, the wall functions, your y plus can still be greater than 30, and you will just do an empirical analysis. You can't really see the slope, but you will guess the gradient itself. So for heat transfer, y plus less than 1 is critical, but for standard flows, y plus greater than 30 is still okay. But again, if exploring the design space is something that you're looking for, you can still get away with the initial analysis of having wall modeling. So for the most part, what type of turbulence models do you want to choose? Again, as I said, if your goal is to figure out what design will work for my particular case and you've not fixed on anything yet, you're still exploring the design space, use K epsilon, do the wall modeling, and converge to a set of design parameters like surface area, inlet diameter, your choice of fluid, so on and so forth. Have a bunch of these objective functions and then try to minimize these all at once or one by one, whichever you want to do. And once you have a good design envelope of, hey, these set of parameters and these set of parameters work for me, everywhere in between, perhaps I can find one optimal solution which may work for different scenarios. And in those cases, you want to do high fidelity or the K omega SST. It's accurate for boundary layers, accurate for separation, which will just work for you in those cases. Next comes the boundary layer, the boundary conditions. For the most part, especially when it comes to industrial applications, the type of inflow that people like to give, this is going to be in flow rate itself or mass flow rates. For the most part, temperatures are not known beforehand, or what amount of heat load is going to come is also not fully known. These are estimated. There is a lot of back and forth that needs to be done, a lot of testing that needs to be done. Understanding the right boundary conditions is a challenge in and of itself, because many times in CFD analysis, at least in the basic templates that we learn from, the boundary conditions are still well known, but in real world scenarios, boundary conditions are really difficult to figure out, because for instance, a simple battery is not going to emit heat at a constant rate. It will emit it at a spike intervals, so to speak. It again depends on how your battery management system is taking the charge away from that cell and so on and so forth. So the heat release rate itself is not constant. So figuring out how to do or how to get that value is a challenge in and of itself. And similarly, the modeling of interface between a solid and a fluid also requires special attention. And many commercial software packages tend to use conformal meshing, so to speak, where the mesh of a solid and mesh of a fluid are going to be exactly connected on nodes with each other. This helps in better transfer of information from one part to another and vice versa. So the conjugate heat transfer we'll just talk about after radiation, but still this is one very important boundary condition that you need to be aware of. Ultimately, residuals. When it comes to non-uniform heat transfer, the residuals will not go down as smoothly as you would like them to be, because your heat is fluctuating in your energy equation. If you're using enthalpy, you're using internal energy, or the temperature itself will fluctuate. This will cause changes in your density through your gas law, whichever you want to use. And once you have changes in density, this causes localized changes in your velocity, which messes up with the mass continuity, momentum continuity, so on and so forth. And in turn, these have their own impacts through turbulence modeling of your K, epsilon and omega, if you are choosing the incorrect boundary conditions of how your turbulence kinetic energy is going to be from the inlet, or how your epsilon is going to be behaving near the wall, so on and so forth. If these things are not, assigned properly, your convergence will suffer. The best thing to do is to monitor an outlet temperature. This is again assuming that you are running a steady state analysis, meaning that over a long period of time, if your simulation has actually stabilized and over iterations, your flow will essentially remain steady, so to speak, or it will not change with respect to time. So monitor the outlet temperature. It should stabilize, it should become flat. The global energy balance, heat in should be equal to heat out. This is the most important sort of takeaway for any CFD analysis, which involves convection heat transfer. So you're performing a high fidelity wall resolved simulation to accurately capture viscous sublayer. What is the target Y plus? I do have a question here for my participants. So when it comes to, Y plus calculation, we still have a correlation through the momentum boundary layer. We have the formula which will give you some value of Y plus. And based on that, the first cell layer height, you will keep your mesh there, and you will run your analysis. But once you post process, once you have fully run your analysis, the Y plus that you find out at the post processing is not going to be equal to the Y plus that you set for yourself while calculating the first cell layer height. Why does that happen? Essentially, the question is simple. The Y plus that you set for yourself initially, and you put your first cell layer height, it's going to work for you initially. And once you solve your CFD analysis, you get the results, and you post the Y plus. The Y plus is not going to be the same as the one that you set for yourself. You'll have to experiment with this for a little bit. Why is that? A velocity field is a very vague answer. Please be a little more specific. I'll be very happy. Velocity field is in the right direction, yes. So yeah, Y plus is dependent on one other property here. This is the tangential velocity, or the shearing velocity that we like to call. Because it is dependent on shearing velocity, the shear velocity is not a constant number. It will again be impacted by virtue of turbulence itself. So as you keep moving in the horizontal distance away from the wall, or across the wall, the parallel to the wall, the Y plus value that you see near to the walls will not be constant as well. And at least closest to the wall where your actual interaction has just started, the Y plus will still be different there because of this, shear velocity or the tangential velocity itself. What is the fix for this? There is not one. Primarily, you need to focus on what is the area of interest and what is the most effective place where you want to run the analysis, essentially. And in those areas, you need to ensure at least your Y plus is lesser than 1. If it cannot be equal to 1 or equal to a certain value, it needs to be lesser than 1 for your wall resolving. For wall modeling, you still don't care, because even if it is greater than 30 and between 30 to 300, it will still work. So there is that. Cool. Oh yeah, sure. Okay, so Y plus is fully dependent on your shearing velocity, or the UT or U tau, what we like to call the tangential velocity. Tangential velocity is velocity that is, just near to the wall, rubbing against the wall, the whole plan there. So closest to the wall, this velocity will be equal to 0, but as you keep moving away from the wall, this velocity will still be higher. The first cell layer height, idea being Y plus is equal to 1, is the area where your velocity will still be in the laminar region. But by virtue of flow being flow, if the bulk fluid motion away from the wall is still highly turbulent, it will have its own impact of impinging on top of the wall or having certain interactions which will cause local acceleration or local deceleration as well. In such scenarios, very specific to 3D CFD here, in such scenarios, your Y plus may not be constant near one location of the wall to other location, so on and so forth. And my primary problem is the Y plus that I set for myself while calculating the first cell layer height is not going to be the same that I see in my post-processing for a steady state analysis, so to speak. So for such scenarios, we need to ensure that we are post-processing Y plus and check in again and again what my Y plus value is, because the local the tangential velocity or the shearing velocity could still be different from what you estimated for your initial case. For the most part, the tangential velocity that we estimate is like a correlation for either a flat plate or for circular pipes and so on and so forth. These may not be valid for the case that you have at your hands, and you may not have the right correlation as well to calculate this ut or u tau value. But yeah, this is the back and forth that you will need to do. I hope that explains it. Or have I confused you more? Okay, super. Thank you. Great. Just the final summary here, and I'll just end it. There are 6 core rules that we need to be very clear on. Your velocity is always going to be the king. The higher the velocity, better the heat transfer coefficient. Your fluid choice is much more important, ultimately, because not just from a fluid dynamic standpoint, fluid is also going to determine the longevity of your product itself. If your fluid is detrimental to the nearby material, it will just eat away at that material, causing leakages, causing failures, so on and so forth. And similarly, having high heat transfer coefficient and a fluid which has higher Prandtl number, not as too high, but just high enough Prandtl number is also quite necessary. For CFD, mesh matters. Mesh matters a lot, because better the mesh, better the results that you will get. If your mesh is wrong, somehow everything seems to go wrong. So make sure, so if your simulation needs to run for 10 days, make sure that or if you want to run a simulation from day 0 to day 10, you want the results to be done within day 10, ensure that you're spending 6 to 7 days on meshing itself, because running the analysis is not the complex part. You just need to monitor it, ensure the right relaxation factors are given. If it is going, if your oscillations are introduced, you can play with the relaxation factors, so on and so forth. But meshing is quite important. When designing a product, prefer your turbulent regime itself. As we've seen, it will enhance your heat transfer. Natural convection is quite weak when it comes to at least the recent products of the Apple Silicon, or at least the ARM architecture, the ones that you have on your phone as well. It's quite easy for them to dissipate the amount of heat, because for them the heat load is still low. So areas where your heat load is still low, you can get away with natural convection. At least people do it with like a vapor chamber, or have different fins or metal railings on the side of your mobile phone, which will help dissipate the heat and so on and so forth. And ultimately, safety is non-negotiable. Whatever product you are designing, ensure that it is tested quite rigorously. And when it comes to CFD, the kind of things you can test for range all the way from effectiveness of heat transfer to ensuring that your battery temperatures or your thermal management is done effectively. And you can also check for the radiation of this heat outwards, so on and so forth. But you can't really check for stuff like amount of noise in the real physical world, the leakages that may come about because of manufacturing defects or the wrong products being chosen, so on and so forth. So that's that. Cool. So yeah, thank you very much. The next webinar will be on next Friday again. This timing seems to work well. So we'll just do radiation heat transfer. I'll talk about the different radiation models that we have. What model will be more complex? What model will be at least give you the answer and not leave you behind? And then we'll just talk about how radiation is necessary for something like the battery thermal management. Good. So yeah, that's it about from my end. If you have any questions, please feel free to stay back. Otherwise, I think we can drop off. Thank you very much for joining.